We're still sketching the proof of the cut-elimination theorem. What's left is to talk about how we would eliminate cuts over compound formulas, cuts between a conjunction and a disjunction, or cuts between a for all and an exists formula. The two cases are actually very similar. In fact, they're so similar that if we'd set up our definitions a little differently, they would actually have consolidated into one case. We already had a high-level sketch of the conjunction case a couple videos ago, so in this video, I'll only talk about the details in the quantifier case. What we're going to try to prove here is that we can eliminate one cut over a quantifier. If for all x phi has rank C, z infinity deduces gamma comma for all x phi with all cuts less than rank C, and also z infinity deduces gamma comma exists in x phi with all cuts less than rank C, then z infinity deduces gamma with all cuts in the deduction less than rank C. And the important point is that in this deduction of gamma, we can't use a cut over for all x phi. All cuts in this deduction of gamma must have rank less than C. So we need to transform these proofs somehow so that we only need to use cuts over simpler formulas. The structure of the argument is still what we outlined earlier. First, we need an inversion lemma. The inversion lemma here says that if z infinity deduces gamma comma for all x phi, then z infinity deduces gamma comma phi of n for any n. The ordinal bound should stay the same, and the numeric bound can't stay exactly the same because n might be big, but the new bound should be the larger of k and n. As always, the proof is by induction on alpha. It splits into cases depending on how the last step in the deduction is justified, and the main case is when the last step is a for all introduction rule introducing for all x phi. In this case, one of the subdeductions is a deduction of gamma comma phi of n, and the bounds on that subdeduction are an ordinal beta n less than alpha, tau beta n less than larger of k and n, comma the larger of k and n. So we use a weakening rule to get a deduction of gamma with bound alpha, comma the larger of k and n. As always, there are a whole bunch of other cases. They're all fairly simple, but it's a lot of tedious work to address all the details and subcases that come up. But notice the idea. Every time we introduce for all x phi, which might be many times because the deduction branches, and there might be contraction rules in it, but every time we introduce for all x phi, we just delete the for all introduction rule and replace it with the branch where we had deduced phi of n. So the main lemma we need is this. Phi is this formula of rank C minus 1. Suppose that for every n, z infinity deduces gamma comma phi of n with the same bound alpha independently of n, and also z infinity deduces delta together with exists in x not phi with a bound beta, and both these deductions have cuts of rank less than C. Then z infinity deduces gamma comma delta with all cuts still of rank less than C. The bounds of this new deduction are a little bigger. The ordinal bound is alpha plus beta, but the numeric bound is h beta plus omega of k, and we'll see in the proof where that new bound comes from. The proof is by induction on beta. It depends on the size of the second deduction, and there are cases for each possible rule that could justify delta comma exists in x not phi. The main case is that we just introduced exists in x not phi. So it's an exists introduction rule, and the previous step is a deduction of delta comma phi of n, and n is at most h beta of k. That's where that new numeric bound is going to come from. By our other assumption, that first set of deductions, there is a deduction of gamma comma phi of n with bounds alpha and the larger of k and n. Using the weakening lemma, we turn these into deductions of gamma comma delta comma phi of n and gamma comma delta comma not phi of n, and then we use a cut over phi of n to get a deduction of gamma comma delta. Since this is a cut over phi, the cut has rank strictly less than C. We pick up this extra plus omega in the numeric bound just to make the accounting come out right. We need tau of alpha plus beta to be less than h beta plus omega of k. If beta were very small, that might go wrong, so we just add plus omega to make sure it's big enough. That's the main case. when the old deduction had deduced 5n and was going to use that to introduce exists in x phi, the new deduction uses a cut over 5n to get rid of that 5n. Once again, the other cases are mostly routine. Except, the way I've stated this lemma, the contraction case is actually going to cause a problem. So in order to make the induction finish, we actually need a slightly stronger lemma to have the right inductive hypothesis. We need to allow the second deduction to be a deduction of gamma together with possibly many copies of exists in x, not phi. Once we've fixed that, the contraction case becomes easy. And in the case we just did, the exists introduction case, there's an additional step we need to take care of these extra copies. The details are in the written notes, but this is still the main idea of the proof. There's something to notice about these bounds. If I have a big complicated proof with lots of calculations, an exists introduction can hide some of that. I can do a bunch of work to show that a number I want exists, and then below the exists introduction, I don't worry about what the exact number was, I just know that it exists. The value is hidden up in some branch of the deduction. When we eliminate the cut over that exists in x formula, we're removing the ability to hide that information. And that's what we're seeing when this numeric bound suddenly gets a lot bigger. We're seeing that this big number that was hidden in the deduction has to get brought out and made explicit.